Hello, I'm Gono Kim from KAIST, and I'm a master's student supervised by Professor Minhyuk Sung. Today, we introduce OptCtrlPoint, finding the optimal control point for Biharmonic 3D shape deformation. As you can see in the teaser image, our method can find the optimal control point that generate more plausible shape variation through deformation. Geometric modeling is an essential for creating virtual 3D content and designing real objects. Yet, creating 3D modeling remains as a tedious and time-consuming task requiring specialized expertise. Shape deformation is thus an important technique that enables producing plausible variation of existing high-quality, artist-generated 3D assets. Due to its importance and broad impact, shape deformation has been extensively studied by the geometric processing community. Specifically, handle-based deformation allows users to edit shape using a set of deformation handles, which are intuitive and procedural parameters directly coming from the 3D models. It parameterizes smooth deformation with a low degree of freedom. With these handles, user can edit the mesh by adjusting the position of handles to achieve the desired deformed shape. Different types of handle have different advantages. There are three types of handle: cage, skeleton, and control point. Among them, we focus on the control point. The control point can provide loose and smooth control that cannot be achieved with cages or skeletons. However, the control point-based deformation is heavily influenced by the position of the control point. As you can see, the rep space suffers from linear artifact, but these disappear after adding two auxiliary control points. Since the deformation result is sensitive to the position of control point, placing the control point to the best position is important. Let me show you a more detailed example. If the control points are located in inappropriate position, it can lead to implausible deformed shape. Conversely, well-placed control points generate plausible deformed shape. We thus aim to find the optimal K-subset of the N source vertices as the control point with target-driven deformation. The optimal set of control point means that it vests with all the target shapes with their corresponding positions in the target. To achieve this goal, we assume that a template mesh, multiple target meshes, and correspondence between them are given. Using these inputs, we want to find the optimal control point that minimizes the average fitting distance between the deformed mesh and target meshes. Now, let me explain the preliminaries. Before we get into the preliminaries, we will explain the notation. X denotes the position of template vertex. The deformed vertex will be denoted as V. The binary selector matrix S indicates the vertex indices of the control point in the template mesh. T is the complementary selector matrix of S, indicating the vertex indices of the template mesh that are not selected as the control point. C denotes the position of the control point. We can calculate C by multiplying S and X. Note that the set of control point is a subset of the template vertex. A is the Laplacian matrix, which is a positive semi-definite matrix used to measure the fairness of X. With this notation, we explain the details about the closed-form formulation of the biharmonic coordinate deformation function. This optimization finds the position of the deformed vertex V that minimizes scared Laplacian energy when the position of the selected control point are fixed to be C. Biharmonic coordinate is defined as the closed-form formulation of this optimization, namely V equals WC. Here, W called biharmonic weight is derived from the solution of above optimization. When the control point and resulting biharmonic weight are fixed, we calculate biharmonic weight only once. Note that the deformation can be computed quickly by prefactorizing TAT transpose. That means we prefactorize matrix only once. However, since we want to find the optimal control point, we need to vary the control point. When computing deformation with different set of control points, it is not feasible to leverage the prefactorization since the complementary selector matrix T varies. That means we need to calculate its prefactorization multiple times. Here, TAT transpose is too large matrix to calculate its prefactorization multiple times. Another challenge is that identifying the optimal K subset from a pool of n elements is an NP-complete combinatorial optimization problem. One possible solution is the exhaustive search that tests all K subsets. However, exhaustive search is impractical due to the typically high number of vertices. So there are two main challenges to achieve the goal. To address these challenges, first, we introduce a reformulation of biharmonic weight that yields the same biharmonic weight matrix W while solving a linear system on a much smaller scale. We also propose an efficient search algorithm that reduces the time complexity while effectively finding nearly optimal solutions. Now, let me explain our approach in details. I will describe our reformulation of biharmonic weight and level of detail control point search algorithm. To address the first challenge, we introduce a reformulation of biharmonic weight. Let M denote the linear system in the original biharmonic weight W. With a derivation involving the short complement, we can rewrite M like this. By replacing M in the initial biharmonic weight, we get the following reformulation. Now, we compare the difference between the original M and new M by our reformulation. Here, SA inverse S transpose is way smaller than TAT transpose. If we set the number of vertices N to 5000 and the number of control points K to 16, we can see that difference is huge. The original M has over 20 million elements, while the new M has only 256 elements. This demonstrates that our reformulation significantly reduces the time required for prefactorization. However, since the Bilaplacian matrix is positive semi-definite and non-immutable, we can apply some techniques handling the singularity of the Bilaplacian matrix A. Thus, we can use shaping up technique or regularization for A. To handle the singularity of the Bilaplacian matrix A, we can apply the shaping up technique. With this technique, the final biharmonic weight is altered slightly. You can find more details in our paper. Instead of shaping up technique, we regularize the Bilaplacian matrix A by adding a small weighted identity matrix, approximating the solution while achieving numerical stability. We choose this method for the experiment. Now, let me explain our level of detail control point search algorithm. Although the computation time of biharmonic weight matrix becomes faster with our reformulation, the exhaustive search is infeasible due to the typically high number of vertices. To address the second challenge, we propose an efficient search algorithm that reduces the time complexity. First, we construct the partition of mesh for effective search. We utilize geodesic various point sampling over surface of the mesh to establish the set of seed points. And then we establish K partition of the mesh by conducting a nearest neighbor mapping of all vertices to seed point using the distance over the volume mesh graph as a measure of proximity. We iteratively refine a set of control points starting from an initial K control point initialized by FPS. When executing our algorithm, we fix the other K-1 control point and only update K's control point. Let me explain the first stage of OptCtrlPoint. In the first stage, we determine the partition to which the kth control point will move. We select one of the sample vertices that provides the minimum sum of distance between the template mesh and all the target shape after deformation when substituting the current kth control point. By finding the vertex with the minimum sum of fitting distance, we identify the corresponding partition region for further exploration. After the stage, we have the best partition L among K partitions. We can find the best kth control point after the second stage. In the second stage, within the selected region L, we find the best vertex similar to the first stage. We calculate the fitting error when substituting the current kth control point and select the one that minimizes the fitting error. The vertex selected during this step becomes the new kth control point for the subsequent iteration. We iteratively refine a set of control points starting from an initial configuration along this algorithm. The time complexity of the first stage is OK squared since we search K partition K times. Assuming an even partitioning of the template mesh with an equal number of vertices in each region, the average time complexity of the second stage is On. When we run whole algorithm, the total time complexity is On plus K squared. Our algorithm significantly reduces the computation time compared to the exhaustive search complexity of On to the K. So we address the first challenge with our reformulation and the second challenge with our efficient search algorithm. Now I will explain the result. For the experiment, we use three datasets containing a variety of characters. SMPL and SMAL are parametric models and used for evaluation, and deformthings 4D represent the real-world case. For human models, we use synthetic shape generated from SMPL. SMPL is a realistic 3D model of the human body that is based on skinning and blend shapes. We use the rest pose as the template shape and generate 1000 random target shapes with SMPL parameter. For animal model, we use 4 classes of shapes, including fox, hippo, horse, and tiger generated from SMAL. The SMAL model is a 3D articulated model that can represent animals, which is inspired by the SMPL model. We use the rest pose as the template shape and generate 1000 random target shapes with SMAL parameter for each template. Deformthings 4D contains characters from Adobe Mixamo and also multiple animated motion for each character. We use 7 animal categories in our experiment. To show the effectiveness of our data-driven manner, we present 2 distinct experimental setups per category and per motion. Per category setup is used for finding the general control point since it involves a wide range of target variations. Conversely, per motion setup is employed for finding the specific control point due to its smaller target variations. For the per category experiment, we randomly sample 1000 different targets from all motion for each category. For the per motion experiment, we use all the frames of the same motion as target. For the evaluation matrix, we use average L2 rows that measures the fitting error between deformed template and target shapes since we aim to deform the template to match the target shape. To show the effectiveness of our proposed method, we compare our method OptCtrlPoints with 3 different baselines. FPS is the case of directly using the geodesic variance point sampling vertex, our initial set of control points, as the final set without searching. Instead of the computationally infeasible exhaustive search that tests all possible subsets, we compare our method with a random search approach. We iterate the random set sampling process n by k times which is significantly larger than the number of iterations in our method. We additionally compare our method with keypoint deformer, which leverages a neural network-based approach to predict keypoint on shape and align template to the target through cage-based deformation. For fair comparison, we train keypoint deformer for each template shape and its corresponding set of target using the released codebase. We show qualitative comparison of our approach compared to FPS, random search, and keypoint deformer respectively. For each example, a white shape denotes the deformed template and a yellow shape denotes the target shape. We also show the raw output deformed source shape colored with vertex-to-vertex alignment to target element for visualization. Notice that our approach finds better counterpoint near joint as shown in the shoulder of the human and achieve better fitting error than other baselines. Compared to random search, our method can preserve detail of hippo's hip. Furthermore, compared to keypoint deformer, which employs cage-based deformation instead of biharmonic deformation, our method excels in fitting the template to the target through deformation. Notably, failure cases of FPS and random search are observed. The legs and body of the tiger deviate from the target shape, while ours preserve fine detail. In the experiment with the deformed things 4D dataset, we highlight the effectiveness of our OptCtrlPoint in discovering the optimal set of counterpoint for a given set of target in a data-driven manner. Our per-motion approach significantly outperforms the FPS baseline in scenario involving larger motion and wider variation in target. Our method achieves much better result in recovering the geometry of the deer's face and legs, whereas FPS falls short in this regard. Since per motion has smaller target variation than per category, our method can find more optimal counterpoint in per motion setup. We conducted experiment with our method with 16 counterpoints. This table shows that our method reduced the fitting error drastically. We also demonstrate the efficiency of our method compared to the naive random search approach for finding a better solution. In random search, we sample subset of vertices n by k times, so it takes day without our reformulation. With the reformulation, the computation time of random search is reduced by almost 1 hour, making it 49 times faster. Our search algorithm results in a significant reduction in computation time, decreasing it from about a day to approximately 3 minutes, while also obtaining a better set of counterpoint as demonstrated in before. Our approach outperforms both FPS and random search in both the per category and per motion setup. Notably, our OptCtrlPoint consistently achieves a lower fitting error in the per motion setup compared to the per category setup. This outcome is attributed to our data-driven approach, which enables us to discover counterpoints that are tailored to the given set of targets. In summary, counterpoints provide high flexibility, but it is challenging to find the best position of counterpoint that can generate plausible deformed shapes. So we introduce OptCtrlPoint, a data-driven method for determining the optimal set of counterpoint to replicate target shape as biharmonic deformation of the template mesh. To address the computational challenges, we first introduced the reformulation of biharmonic weight that can solve a linear system on a much smaller scale. And our efficient search algorithm reduced the time complexity from O(n) to the k to O(m) plus k squared. We show that our algorithm significantly outperforms the random search in terms of both quality and time efficiency. In future work, we plan to extend our method to identify lesion handles of 3D shapes. In OptCtrlPoint, we assume that the correspondence between template and target shapes are given. We'll further extend our method if the template shape and target shapes are heterogeneous. We thank to all support for our project. You can access our project page through this QR code. If you have any question on our project, please contact me. Thank you for your attention.